all the data come on your light curve. So this is what we should try to do now with this talk. So this is our goal. OK, now, this is the outline of the talk. So we will start with the algorithm for finding the best model. So downhill methods, and then I will speak about Markov chains. And immediately after, once we have found the best model, we have also to assess the uncertainty because we are doing science. And so we need to do provide the uncertainties of our models. Then we will see, that, as also Scott introduced in his talks, actually there are many degeneracies which make the problem very difficult in microlensing. So I will speak about degeneracies. And then immediately after, I will introduce Bayesian analysis, which is something connected to fitting, because sometimes there is not enough information in the data to decide what the mass of the planet, for example, is, and you have to inject some prior assumptions. And finally, at the very end, it seems funny to see initial conditions at the very end, but actually this is the worst problem we have in microlensing. So finding the initial guess for our fits. So it will come as the last step in this talk. OK, so let's start with the basic stuff. Also, Scott introduced that if you want to find the best model, you have to rank models according to some estimators. And in practice, what you do is that, well, let's see how likely is to get this data yi from this model f. And this is the so-called likelihood. So in practice, this is just the probability that for a given model f, you get the observed data yi. So you can see that this is actually the opposite way you would. So this is, in principle, you would like to find the model given the data, but it's actually the opposite. So the probability of obtaining this data given this model. So the likelihood is just is this thing. So it's the opposite of what you would like to have. So the probability of since if the measures are all independent, you can write this probability as the product of the probability of getting every individual data from the model. If the measures are independent, you can write it this way. And then if you have Gaussian statistical errors, all this probability will be Gaussian functions, and then this product enters the exponential as a sum. And so in the end, you will end up with this function here, which is the so-called chi-square. So the most likely model for your data is the model that maximizes the likelihood, which is the same as the model that minimizes the chi-square, because the minimum of the chi-square will be the maximum of the likelihood. So the chi-square is just the difference between the data and the prediction of your model divided by the statistical uncertainty of your measure, and squared, of course. So after all, if you want to find your best model, you need a minimization algorithm for the chi-square. And in the end, the chi-square is just a function of the model, a function of the model and its parameters. So in the end, the chi-square is just a function living in this multi-dimensional space. If in the case of microlensing, you have 7 parameters for the binary lensing. If you also need to introduce parallax, you have 2 more additional parameters. And if you need to introduce orbital motion, then you have several possible choices and several possible approximations. You can end up with many, many parameters. So the problem is not trivial at all. In addition to these 7 parameters, as Scott said, actually we also have the source and background flux for all the telescopes participating in the observations, because these data sets typically are uncalibrated. Even if they are calibrated, of course, you don't know what part of the flux is in the source and what part is in the blend. So in principle, you also have 2 more parameters for each telescope, but luckily they come linearly. So actually, this is just a linear function, and you know how to fit a straight line in on the data, you just have to use the least squares fit method. So this is just least squares fit formula, standard formula that you probably seen in your first year of at the university. So actually, these two parameters can be estimated analytically once you have the model, which actually which depends on the 7 parameters of your binary lens model. So these 2 parameters are not a problem. We can go ahead without concerning too much about that. Okay, here you cannot read, but it's, now we need a minimization algorithm. So let's go and find a minimization algorithm. You can do several things, but of course the easiest thing you can do is just calculate the local gradient from your initial condition. So once you are in a point in your parameter space, you can calculate the gradient of the chi-square. So the gradient of the chi-square, doing some algebra here, depends on the derivatives of the model with respect to the parameters. For the single lens case, you can calculate these derivatives analytically, and Scott has shown them in his talk. For the binary lens case, you cannot do that analytically. So actually calculating these derivatives requires finite difference. So it means that you have to run your calculate another light curve with just a small difference and then take the difference. That's the way to calculate these derivatives. Anyway, once you calculate the gradient of the chi-square, then the thing you have to do, just move in the opposite direction, because the gradient climbs up, you have to go the opposite direction if you want to find the minimum of the chi-square. And so you just take, as the next step in your fit, the initial point minus the gradient with some coefficient alpha. And this coefficient always is determined by the search along the line, typically. If it is too large, then you are overshooting your minimum and you go the other side. If it is too small, then you're progressing very slowly. So it has to be tuned. So this is a very basic algorithm, but there are other more sophisticated algorithms. For example, this Gauss-Newton method, which is more or less the one that Scott mentioned. So in this case, if you start from a point and you want to find the offset so that you end up in a minimum, you just impose that. So impose that the new point is the minimum. So if it is a minimum, the gradient should vanish. So you impose that the gradient must vanish at the new point, and then you tailor expand a bit in terms of delta. If you're close enough to the minimum, then you can tailor expand your model. You get this equation with a bit of algebra. In the end, you have a set of linear equations for delta. So it's just a set of linear equations for delta that you can solve with standard methods. And in the end, you will find this offset delta from the minimum. Of course, you will not find it in one single step, because it is would be possible only if you are in a perfect paraboloid. But we are not in a perfect paraboloid. But nevertheless, this method is much more efficient than the steepest descent method we have seen before. Okay, then actually we can combine the two methods. And this has been done by Levenberg. So the Levenberg method is a combination of these two methods. So the modification proposed by Levenberg is this. So it's the addition of this term lambda delta in the linear equation. So if lambda is very small, so this term is negligible, then you work with the Gauss-Newton method, which is very fast. But if you are very far from the minimum, the Gauss-Newton method will fail. And so you have to move to the steepest descent method. And this is done just by increasing the value of lambda. So if lambda is small, then you go back to Gauss-Newton method. If lambda is large, actually this term dominates, and then this becomes the steepest descent method. So in one set of equations, you have two methods, and depending on the value of lambda, you can go from one method to the other. Okay. There is a further optimization of this method, which is called the Levenberg-Markov method. This takes into account the fact that if your gradient is very shallow, if you're in a very shallow surface and the gradient is very, very small, then your progress will be very, very slow. So in this case, it's better if you normalize this lambda term with the ji squared, so the gradient squared. So if the gradient is very small, this will go down to the denominator when you invert the equations, and then you will get a boost in your feet so that it will not move slow, but it will actually move fast, so that they will go much faster than with the steepest descent method. So in this way, everything this method is made much more efficient. And in the end, the Levin-Markov method is one of the best methods we have for minimizations after all. So it proceeds like that. So you start from an initial value of lambda close to 1, and then you calculate delta in your first attempt, and then if you get an improvement in your chi-square, you accept the new point and decrease lambda, because it means that you are close to the minimum, so you can go to the Gauss-Newton method. If the chi-square is not improved, then we reject the new point and increase lambda. So we rotate toward the steepest descent method, which is safer, because it just calculates the local gradient and then moves downhill. Okay, so if you want to implement your Levin-Markov, you have to calculate the gradients, and as I said before, you have to calculate the derivatives, which is the lowest step. Then the linear equations can be solved by standard methods, Cholesky decomposition, Gauss method, whatever. And it's a very fast method and a very robust method. The only thing is that, of course, if you end up in a local minimum, you have no way to exit this local minimum, and so you are not the exploration that you do with the Levin-Markov is very, very local. You're not exploring the parameter space. You're just getting the closest minimum to the initial condition you're starting from. So actually, there is some tricks in order to exit from a minima. So this is one trick I implemented in my code. So once you get stuck into a local minimum, what you can do is to add the penalty function to the chi-square. So you modify the chi-square by adding this penalty function. So in this case, the minimum is filled up, and so if you run the algorithm again, it will possibly move to another minimum. So this is a way to enlarge your search. So instead of finding only one minimum, you fill up the minimum and then run again the search, and so you can find another minimum possibly, and then you can widen your exploration. Okay, moving to other methods. This is also a quite popular method, this downhill simplex method. In this case, you start with a family of m+1 points, and then where m is the dimensionality of the parameter space, and then you calculate the barycenter of the best m points just by removing the worst point, and then you calculate the reflection of the worst point with respect to the barycenter. So you replace the worst point with its reflection with respect to the barycenter. So in practice, this will make the simplex move toward the best direction. And of course, this can be, you can tune this coefficient gamma in order to have an expansion or contraction. There are rules to do that. And so in the implementation, you can find in the literature. And in this case, there is no need to calculate the gradients. In principle, it moves slowly with respect to the Levin-Markov, but since it doesn't calculate the gradients at each step, actually it moves. Each step takes much less than Levin-Markov, even if each step is shorter. This is another method, differential evolution, which is the favorite one for Etienne Bachelet, and this is possibly the one that you will use later for the fit of your microlensing light curves. So in this method, you start from a population of so-called agents, with a population which is at least as large as 4, but of course this is something that can be tuned in the code. And then at each step, you make an evolution of this population. How do you evolve this population? So for each agent, you pick 3 more random agents, A, B, C, and then you mix everything up. You mix the the coordinates of these these agents, and so you get a proposal a candidate new agent y. So once you have the candidate new agent, if the chi-square is improved, then the new agent replaces the old one. So at each step in the evolution, some of the agents will be improved by this method. Some of the agents will not be improved, so it will be kept fixed. So and at each step, your population evolves, and of course, it will evolve towards lower chi-square. And this is a way also to explore also a region of the parameter space. Now let's move to the Markov chain Monte Carlo. Scott said, and I agree with him, that actually Markov chain Monte Carlo is not a minimization method. So even if the people are, now there is this misconception, actually this is not a minimization algorithm. This is a way to sample a probability distribution. So after you sample your region, in the end there will be one best model, and so you will find something. But typically typical Markov chains are done with 10,000, 100,000 points. So you're really doing a lot of work for something that you can do very quickly. So in this example, for example, from this point, the Markov chain here was going downhill. And after 10,000 points, it's the best model in the Markov chains was 3 to 10 to minus 3 accuracy with respect to the true minimum. But the same accuracy is reached by steeper descent in just 8 steps. So you don't want, if your purpose is just find the best model, you will not use the Markov chain. You will use another algorithm, or like the ones that I presented before. Otherwise, you will waste your computational time for nothing. Okay, how does a Markov chain work? So, well, probably most of you know how a Markov chain works, but it's better to repeat if some people don't know. So the idea is that once you are in the point xn, we draw a candidate new point y using a proposal probability distribution q. Now this is a function, we will spend a whole slide about this function here because it's very important. But assuming you have this probability distribution, then you draw a candidate new point, and then if the probability of this new point is better than the old one, we accept the proposal, and so the next point in the Markov chain will be this candidate y. If the probability of this point is less than the previous one, we don't reject it outright. Actually, we can accept the proposal with the probability which is given by the ratio of the two probabilities. And if the candidate is rejected, then the new point in the Markov chain will coincide with the old one. So you will have duplicates in your Markov chains. Your Markov chain will actually be full of duplicates. But actually, this is not bad, because there are theorems that ensure that if you follow this procedure, after you have a large number of points, then this Markov chain will be a representative sampling of the probability distribution. So it seems strange, but actually this is what mathematicians say. And of course, you have to discard the so-called burn-in phase when you are still far from the minimum. So this has to be removed from the Markov chain in order for this to hold. Of course, if we want to optimize our chi-square, our model, we have to set this p, this probability distribution, will be the likelihood. So we will use the likelihood as the probability distribution we want to sample. Now, let's go back to this proposal probability distribution. Now, the choice of this thing is quite crucial for the efficiency of the Markov chain. And you cannot change it during the Markov chain. This is forbidden. Otherwise, the final result will not be a representative sampling of the probability distribution. So you cannot change it during the Markov chain. Well, what can you do? Well, you can just use a uniform box centered on your data point. You can use a Gaussian, whatever, but the shape is not important. What is important is the size of this probability distribution. Because if your proposal is too far from your point, then probably you are going in a region that is completely excluded, the region which is very unlikely. So your Markov chain will never accept new candidates because your candidates will be too far away. But if, on the other hand, your proposal probability distribution is too small, then your exploration will be very local, and we will not explore all the available region in your parameter space. And so your Markov chain will never reach convergence. So you have to balance between the two opposite situations, and you have to choose something in the middle. So in principle, there are prescriptions for that. You have to set up the size of your proposal probability distribution in such a way that the acceptance rate should be in this range, between 0.2, between 20% and 60%. This is the prescription. And if you go to large dimensions, such as in the case of microlensing, there are theorems saying that the optimal acceptance rate is 23%. So this is the optimal one. But in principle, everything between these is more or less reasonable. Okay? So if you're getting 1%, that means that your proposal probability is too large. You have to make it smaller. If you're getting 100%, then your probability distribution is too small, and then you have to enlarge it a bit. Okay, and of course you can adapt its shape by the local study of the gradient. So you don't take the same size in each dimension because they are also physically different variables. Okay, you can check the convergence of the Markov chain. This is quite straightforward. In principle, what you have to do is to divide the Markov chain in different chunks, and all chunks should represent more or less the same distribution. And there are measures for that. There are autocorrelation measures that can be set up. There are many ways of estimating the convergence of the Markov chain analytically. I will not go into this detail. One thing of the Markov chain is that since you are able to climb up your chi-square surface a little bit, you can jump out of local minima sometimes, and then this explore another minimum, but this means that also the convergence may be quite problematic in some cases. Okay, now if you want to enlarge your exploration, then there is a way to do that with the Markov chains, actually. And this is a technique that is now known from 30 years, I think, something like that. This is so-called simulated annealing. This simulated annealing is just this. You can modify your likelihood by including this temperature T in this denominator. And you can imagine that if your temperature is very, very high, then the argument of this exponential will go to 0. And so your probability will be 1 everywhere. That means that your Markov chain is free to move all around the parameter space. So at high temperature, you will explore a large portion of the parameter space. At some point, in this way, you can find many possible candidate minima. And then if you want to explore them more closely, you can go down with the temperature. You can decrease the temperature gradually, and until you go down to T equal 1, which is, in which case you are starting to sample the likelihood, what is the correct likelihood. So, for example, in the same example we had before, if we had a T equal 1 here, we just catch this minimum, but we miss the other minima. So if instead we decide to start with a high temperature of T equal 10, then our exploration will look like that. And of course, in this case, we realize, oh, there are 3 different minima, and so this is the best minimum. Let's do an exploration here, and then you can start from the best model found from the first Markov chain at high temperature, and then, of course, in this case, your final Markov chain will sample the best minimum. So this is a way to explore a wide region in the parameter space with Markov chains. Okay. That's all about finding the best model. Now let's move to the next topic, which is the assessment of the uncertainty. Now, once you have your Markov chain, you have a sampling of your probability distribution. So you can build histograms on whatever parameter you want. So this is taken from a real fit of a microlensing event in which you have distribution on 7 parameters. And you can see how this distribution are more or less Gaussian, save for the source radius, because in this case the source radius was unconstrained because it was not a caustic crossing event. So the source radius was basically unconstrained in this case. So once you have this Gaussian distribution, you can immediately guess the uncertainty from this distribution. In practice, what people do is to build confidence intervals. So there is a prescription for that. In practice, you start from the highest bin, and then you go down until you get as many points as you want, for example 90%. And so for example, if you want 90% of the points, you stop here at this level, and so the left side and the right side will define your confidence range. And so this is a way to obtain uncertainties for Markov chain. With Markov chains, you can also build correlation plots with, by combining 2 parameters together, and these are very useful. You can draw contours also, in this case, in confidence level contours, including 90%, 95%, or whatever of your points. And this is very useful also to visualize the degeneracies. So the degeneracies are visible here in cases in which you have correlation between 2 parameters. This is Q, the mass ratio, and this case is correlated with T. I think this is T naught. Yes, the T naught. So you can see the correlations you have in your fit, and so you can visualize the degeneracies. There is an alternative in order to derive the uncertainties. If you don't have a Markov chain, you can use the Fisher matrix. And there is a common misconception that the uncertainties derived by the Fisher matrix are wrong. They are underestimated. This is not true, actually. Because after all, the Fisher matrix is an analytical approximation of the minimum by a paraboloid. So in most cases, in all cases, it will be of the same order of magnitude of confidence intervals estimated by Markov chains. And in most cases, it will be very, very similar. So the Fisher matrix is just a matrix of the derivatives of the model calculated in this way. And so it turns out that the covariance matrix is just the inverse of this Fisher matrix. And in the end, you can read the variance of each parameter along the diagonal of this matrix. So this is a very quick way to assess the uncertainties once you have the best model, whatever the minimization algorithm you use, even if you don't have your Markov chain. And for example, in one of these probability distributions, so the confidence interval from the Markov chain is in blue, and in green is the result from the Fisher matrix. So you see that they're very, very similar after all. So in the end, since we are just estimating the uncertainty, so this is fine. OK, now let's start to see what is bad with microlensing. So what is the problem with microlensing? The problem is that we have many, many kinds of degeneracies. So you have a degeneracy whenever you have the same data can be actually explained by many different models with the same likelihood. So in that case, you cannot decide which is the best model. We can have continuous degeneracies or discrete degeneracies. You can also distinguish 2 types of degeneracies: strong degeneracies, which are just coming from the fact that gravitational lensing in physics is degenerate. Or there are also accidental degeneracies, just coming from the fact that your coverage of the microlensing library is not complete. And so if you have gaps, you can put any kind of structure in the gaps, and this will not be contradicted by any data. So in this case, you have a degeneracy, an accidental degeneracy. OK, let's see some of these degeneracies. Discrete degeneracies. So this is an example of a closed wide degeneracy in planets. This has already been discussed many times. So the central caustic is invariant under the transformation S going to 1 over s. So this is a degeneracy, a structural degeneracy of gravitational lensing. You cannot do anything from that. So there is also a closed wide degeneracies for binaries, because in the wide limit and in the closed limit, the caustic are also the asteroids with 4 cusps. So this is the so-called Changer-Refsdal caustic in the wide regime, and the quadrupole caustic in the closed regime. They're practically identical. So in this case, the light curve will show up with 2 bumps, or 1 bump and the shoulder. And in practice, you can reproduce the same light curve, but all trajectories grazing 2 cusps in any possible order. So in principle, you have 4 possible cases in the wide regime and 4 possible cases in the closed regime. So in this case, you have many, many possible minima. Furthermore, there is this Hahn and Gaudy degeneracy for the high magnification case, in which you can replace the planetary central caustic by a closed or wide binary caustic, because after all, you just see these 2 bumps here, and so you can obtain them in 2 different ways. And so you can have a situation in which a planetary solution is degenerate with a binary one. And of course, you have also all possible subcases, as said before. But there are also other degeneracies which are less studied, but appear everywhere in binary microlensing, because after all, in particular, when you have an intermediate binary, you can cross the caustic in many, many possible cases, and more or less the light curves will look quite similar. So in this case, for example, you have 2 different trajectories that give the same light curves. So it's typically quite difficult in particular, if your coverage is not complete, to distinguish these cases. And furthermore, you also have the satellite degeneracy. If you have also observations from space, this is the degeneracy you also have for the single lens case. In some cases, the binary lensing is able to break these degeneracies, because these trajectories will possibly meet a caustic, and so can be distinguished. But in some cases, they remain. So in particular, when you are studying high magnification events in which the central caustic is more or less is very small. Okay, some examples of continuous degeneracies. The size of the asteroid caustics depends on this combination in the wide regime. So in the wide regime, the size of the caustics is given by a combination of S and Q in this way. So in practice, what happens is that if your trajectory is actually close to this caustic, it's difficult to understand whether this is due by a planet and S is relatively small, or by a binary, so with a larger mass ratio but a larger separation. So in this case, you can have very long degeneracies in the SQ space. Here is S, here is Q. So it's difficult to disentangle the mass ratio from the separation. Okay. In principle, see, the exploration of these continuous, very long continuous valleys is very, very painful. So you can imagine how difficult it is to explain to explore by Markov chain all these valleys. You can see that this Markov chain didn't go as far further than 8 separation in Einstein radii, but actually the degeneracy was continuous, practically almost to infinity. So in these cases, we can set up some tricks. One possibility is that we rotate the box of proposal distribution, and this can be easily achieved if you diagonalize the Fisher matrix before starting the chain, so that you set up it, adapting it to the degeneracy. But this only works if the degeneracy is linear. If the degeneracy is non-linear, then this trick doesn't work. And what you have to do, you just have to choose different parameters. If you choose different parameters, such as these ones, then this banana shape here will become more or less straight. And then this trick will work. So going to new parameters is sometimes useful in order to explore these continuous degeneracies in the nonlinear case. Other tricks, you can define the origin of your coordinates at the center of the caustic we wish to study, so that we don't have degeneracies between UZ, U0, T0, and whatever. Other tricks fit the log of some parameters. So since S and Q may vary over orders of magnitude, sometimes it's better to fit the logs of these quantities. And otherwise, you can use combinations that are clearly established by the data. For example, if you know the time of a caustic crossing, you can take this time of a caustic crossing as one of the parameters and then define all the other parameters with respect to these parameters. Or, for example, the source crossing time, which can be quite easily estimated from the sites of the caustic crossing. So these are a possible alternative parameterization. I want to mention also this one by Cassan. So Arnaud Cassan proposed to use the time of the caustic entry, the time of the caustic exit, and then the curvilinear abscissa along the caustic as two additional parameters. In this way, all the geometric parameters U0, alpha, T0, and T are replaced by these four parameters, which are clearly established by the light curve. So this is a way to fight against degeneracies when you have very bad situations. Okay, well, this is a slide with other pieces of information. For example, in principle, the TE, the Einstein time in the PSPL light curves is in a degeneracy with U0 and the flux of the source star. But typically, in binary lensing cases, actually, the Einstein time is fixed by the sides of the caustic. So the sides of the extension of the caustic crossing is an indication of the Einstein time. So typically, this breaks this degeneracy, but couples the Einstein time to other variables. Another nice thing to know is that if you have a planetary model that mimics a binary model, typically they come at different blending levels. So, and this can help you, because if you have a planetary model and binary model for the same event, typically they will come with different blending levels. And so you can say, okay, if this comes at negative blending, probably this is not a physical model. Okay, other models may predict unlikely source radii or unlikely Einstein time. So at this point, we can start to think about injecting some external information. So we can derive models, explore our parameter space, but some of these alternative minima will lead to unphysical solutions, or at least unlikely solutions. So at this point, we have to discuss unlikeliness of models. So how do we quantify unlikeliness? How can we say, well, this source radius is unlikely? We will never observe something like that. At this point, we can combine this external information, the likeliness of measuring something, with our fit. And this is done with the so-called Bayes theorem. So in principle, we can just say, okay, our parameters will vary in this interval. For example, we will never observe a source radius larger than 1 in Einstein rings. So this is easy to implement, because you just have to set boundaries of your parameters. This is so-called the uniform prior. So you're just setting a boundary, a lower and upper boundary to your parameters. This is, in practice, automatically implemented and easy to do. But actually, this prior information can be injected in a more sophisticated way, because after all, we know that microlensing events come from stars that are in the bulge, that are lensed from stars that are either in the bulge or in the disk, and these stars should obey some properties, some luminosity functions, mass functions, spatial distribution, velocity. So there is a lot of information that is already available. So we can say that, use this information and establish whether our model is likely or not. So the way to combine this prior information with the likelihood we have for the given model is to use the Bayes theorem. So the Bayes theorem states that the posterior probability, so the probability that of having some parameters for the given data set, can be expressed as the product of the probability of having the data given the parameter, which is the likelihood, so this first term is the likelihood, times the probability of observing those parameters, which is the prior probability distribution. And everything is divided by some normalization factor. So how do we implement the Bayes theorem? This is quite straightforward in Markov chain Monte Carlo, because you just have to modify the probability distribution. Instead of sampling the likelihood, you just multiply the likelihood by the prior distribution, and that's all. Then you are no longer sampling the likelihood, you are sampling your posterior probability distribution. And so in the end, you will end up with the posterior probability. The normalization factor cancels out because we're always dealing with ratios, so this is not a problem. So if you have two minima that are more or less at the same level of likelihood, but your prior favors one of those, your posterior probability will say this is the correct solution, while this one can be excluded by our prior information. And so this is the way to go if you want to exploit this prior information and to decide which of the all possible models you have are physical and which ones are not physical. Okay, how do you choose priors for your microlensing fit? Then at this point, you must use information from some galactic models. So there are several choices. Here is just a list of references. You can check Dominic, the Besançon model by Annie Robin. She will probably speak about that later. And also, other information that can be injected is further constraints you have, for example, from independent measurements. So, for example, if you have constraints from the blending light, from adaptive optical observation, you can inject it at this level in the same way. Okay, now we have exactly 0 time for the initial conditions problem. So I will try to be as fast as possible. Now, the problem is that all the things that I've said up to now assume that you have already close to the minimum, which is not easy, as I told you before, because you know there are many possible degeneracies, and the microlensing space is huge. So starting from an arbitrary point will never give you the correct solution in practice. So you need a theory of initial conditions in order to choose the correct initial conditions. Now, if you have data coming from the observations, then in principle, if you want to make a search as broad as possible, there are 2 possible ways: a grid search or using a template library. Now, as for grid search, this is just quite trivial, because you just scan the parameter space and run fits from each point in this grid. And of course, you can start many Markov chains or whatever algorithm you're using from each of these points, and some of them will just never converge like these ones. Some of them will end up in a local minimum, but there is still the possibility that some minimum will be actually missed by this approach, because of course everything depends on the sampling of your on the pace of your grid. So if your grid is too coarse, then it may miss minima, like in this case. If it is too dense, of course, you will have a lot of redundancy, because many fits will end up in the same minimum, so you will discover the same solution many times. So this is not, you can imagine that this is not the most efficient way to search in the parameter space. You can make it more efficient by doing a 2-steps grid search, exploiting the fact that magnification maps can be reused many times. First, at fixed S and Q, you make a grid search in the other parameters, and so you find the best solution for a given SQ, and then you do the same for many possible pairs of SQ, and at this point, the search can become quite fast. There are codes available for the approach along these lines, so the map, BIC, this is public code that can be used following this kind of approach. Well, the alternative, if you don't want to do this brute force grid search, is to start from a clever initial conditions. So after all, what we have to do is to match some light curve to the data. And after all, what we need to do is to build a library of all possible morphologies of light curves. And this is an approach that was first proposed by Di Stefano and Maun in 1996. It has been developed in many flavors. But the problem is that it is difficult to make a full catalog of light curves in binary microlensing because the phenomenology is extremely broad. So the most systematic exploration has been done in 2015. Actually, it took 2 years or more to do that. But and then 73 different morphologies has been found in 232 regions, and the search was limited to equal mass binaries, so without even changing the mass ratio. So we still don't know how many possible microlensing light curves you can have for the generic parameter space. And in this case, the search was done by scanning the parameter space and then identifying all regions with the same number of peaks. So the black region is with 1 peak, this dark blue is 2 peaks, then 3 peaks, 4 peaks, and whatever. And so in each of these regions corresponds to a different morphology. So as you can see, the number of possible shapes of microlensing light curves is huge. So how can you exploit, once you build a template library, how can you exploit them to set up your initial conditions? The thing is quite, well, it's tricky in some sense, but I will not enter the details. So the prescription is quite simple. You have peaks in the data set, and you have peaks in your template library, in your template. So what you have to do is to match the peaks in the data with the peaks in your template. Once you have this, in practice, you fix the time scale of your event and the time t0 of your event, while all the other parameters are taken from the template. So, and this will give you the initial condition for your fit. You repeat it for all possible morphologies, and you will have a searcher throughout the parameter space of microlensing. So that's the idea. So, of course, there are microlensing. If your data only contain 1 peak, you have to replace the second peak with something else. For example, the time of the anomaly is the easiest thing to do as a position of the second peak. So this is the approach that is followed in the RT model, which is an automatic platform for real-time modeling. So this code works automatically every time new anomalous macrolensing events are discovered, and you can check the web page in which you will find the models are posted in real time every time they are calculated, and so you can, yeah, we have to close. Yes, this is the last slide. So in this data, in this case of RT model, the data are taken from Artemis, which is another platform for modeling, but only for the single lines modeling. And so this RT model uses matching from a library of 244 templates. So after all, not a huge number, much less than any grid you can imagine. Much less than any grid you can imagine in a 7-dimensional parameter space. So, and it is a clever choice of templates. So and all of them are inequivalent. That means that you don't have too much redundancy in your search. Okay, and then for each initial condition, the Levin-Markov fit is done, and it is repeated 5 times using the bumpers method in order to enlarge the search. The calculation is done using VB binary lensing, of course, and all models are ranked by their chi-square. Duplicates are removed if they fall within the same covariance ellipsoid, and then models are posted on the public web page. And it runs, you cannot read it, it runs on an 8-core workstation, so a single computer, not a cluster. And it can do everything in taking 2 hours per event. Okay, so let's get an outlook to the future. So we have seen that even in equal mass binary, we have many, many regions in the parameter space. If we include the parallax, orbital motion, then we can have more morphologies coming out. So it's really discouraging in some sense that there are so many possibility microlensing. And if you include these new parameters, then the grid searches will become unfeasible. And so, but nevertheless, template libraries require also a long construction, a long exploration of this parameter space. The same holds for triple and multiple lenses. So for triple lenses, also running grid searches may become unfeasible. And so we need a clever approach also in this case. So in view of WFirst, of course, we need to improve our automatic modeling capabilities because we need to model most of the microlensing events more or less automatically. And that's why this software is being developed, PyLima and MuLens model, two different approaches to this problem. So this software will be very important to provide tools to fit more in an easy way all this huge amount of light curves. Okay, I think I can stop here. Yeah, of course. This is just an implementation of a grid search, starting from a coarse grid and then going down. Yeah, in principle, I think people doing grid searches use something like that, more or less. So they go to finer grids when they want to make sure that they get everything, all solution. Of course, if you start from a very coarse grid, it may happen that deep minimum, but which are very narrow, may be completely missed by a coarse grid. So the problem with grid search is that actually there is always the possibility that there is something between your cell, your grid cell. So the alternative, I prefer the template matching because you're putting an initial condition in all possible regions in the parameter space with inequivalent morphologies. So in some sense, you're covering everything, even the very small regions that would be missed by the grid search. That's why I think it's preferable.